Welcome back to the channel and to our stupid simple small engine fuel injection project. So right away, let's be clear. This is stupid simple and it's not going to be perfect. We're going to be ignorant to a lot of important things in order to keep this simple. So go ahead and adjust your expectations just a little bit. Well, perhaps adjust them a lot more than that. So first of all, we're going to be using an Arduino microcomputer, but I assure you, this is not anything close to a Speeduino fuel injection system. Nope, as a matter of fact, we do have a Speeduino NO2C EFI fuel injection system that actually has seen a lot of action on the Predator 420cc
Big block
powered Honda Insight. The Arduino-based Speeduino EFI system was definitely cool, and we got the big 420cc Predator engine up and running in no time. A fuel-injected lawnmower engine? Yep, we did it, and best of all, the Speeduino used Tuner Studio software, so tuning the big one-cylinder engine was a breeze. You know, for small engine EFI, the Speeduino was definitely the way to go. But we ain't doing that today. Instead, we're going to try something different, and we're going to build a very primitive fuel injection system. You know, just to see if it can be done. So we are going to cheat a little bit and use the Arduino for development purposes. But if all goes well, we may be able to replace it with a 555 timer circuit. We'll see. So ultimately, the plan is to use a General Motors map sensor to pretty much regulate the amount of fuel that gets injected. It's definitely a bit sketchy, and like I mentioned, it won't be perfect, but it's worth a try. So this stupid simple fuel injection system is based on the original Bosch CIS fuel injection system that was popular on European cars in the mid-70s. Now, CIS stands for Continuous Injection System, and in the mid-1970s, the Bosch CIS fuel injection system was about as simple as it gets. And keep in mind, the early systems didn't have an O2 sensor, so there was absolutely no feedback to the system. Now, this is a diagram of the early Bosch CIS system, and it's super complicated to look at, so I'm going to simplify it. But first, this is the fuel tank, the fuel pump, the accumulator, and the fuel filter. We don't need to look at this. Basically, this is the high-pressure fuel stuff. And boom, I got rid of all the stuff we don't care about. The high-pressure fuel goes in here. That's all we need to know. The intake air goes into here, and the air for the engine goes this way. Of course, this is the injector. All right, let's zoom in. Nice. Okay, let's simplify it again and put the injector in the intake manifold. So on the Bosch system, the injector is mechanical, and when the engine's running, it continuously sprays fuel all the time. It's not timed and it's not batch fired. Nope, it sprays fuel all the time. At idle, it'll spray a tiny bit of fuel, and at full throttle, it sprays a lot of fuel. The amount of fuel that it sprays is determined by this sensor plate. Basically, this is a mass airflow meter of sorts. The air going into the system will push up on this sensor, which is connected to this arm, which then modifies the fuel pressure going to the injector. The more air that flows past this sensor plate, the more fuel gets sprayed at the injector. And keep in mind, the fuel sprays continuously. The Germans figured this out back in the day, and it worked pretty good. I had an early Volkswagen Rabbit with this system, and a few BMWs basically with the same system, except they had the oxygen sensor and frequency valve for precise air-fuel mixtures. So this system doesn't have a crank position sensor, it doesn't have a throttle position sensor, it doesn't have an air intake temperature sensor, and on the early systems they didn't have oxygen sensors, although the later systems did have them. It did have a thermal time switch for the cold start valve, and it had this doohickey that allowed a slightly richer mixture during warm-up. So if you ignore the thermal stuff for warm-up, basically the only sensor this uses is the mass airflow sensor. The bad news is, well, there's no way we can use any of this stuff on our small engine, and we're going to have to improvise. So we're going to get rid of this thing and replace it with a map sensor. And of course we'll get rid of the mechanical injector and replace it with a modern electric injector. The plan is, this injector will operate at a fixed frequency, like 30 Hz, and the Arduino is going to read the map sensor and calculate the duty cycle for the injector. At idle with no load, the duty cycle will be very short, and at full throttle with a full load, the duty cycle will be a lot longer. You know, if you squint your eyes, this simple EFI system very much resembles the Bosch CIS system from long ago. But Jimbo! Yeah, I know. Believe me, I know. But you need to remember, we're building a very primitive fuel injection system. I'm definitely aware it's not going to be perfect with just a map sensor. I reckon there's a reason for field tables and hundreds of calculations just to make modern EFI systems work. I've been there and I've done that, and I've spent countless hours tuning EFI systems. This is definitely going to be sketchy, but I think we need to experiment and see how close we can get. Anyway, for the high-pressure fuel pump, we're going to be using this guy. It's made for a 2-cylinder fuel-injected Kohler lawnmower engine. This port is where the low-pressure fuel goes in, and this port is where the high-pressure fuel comes out. This pump has an internal pressure regulator, so we can expect between 38 and 42 psi from this thing. And this last nub is for the vent tube. Now this pump has an internal float with a needle and seat just like a carburetor, and you're not supposed to gravity feed these pumps. Instead, this pump is expecting fuel to be delivered by a vacuum pulse type fuel pump. So in essence, you need a fuel pump for your fuel pump. Now this guy was fairly cheap, and it was $53 on the Jungle site. It's definitely cheap, and it will leak fuel if you gravity feed it, so don't expect much. The injector is from a GY6 clone and it cost $27. The reason I picked this is, well, it was cheap and the fuel line barb is built in, plus it has a boss for a mounting screw. We used this same type of injector on the 420cc Predator with good results, so we're going to try it again on the 212cc Predator. This guy uses a standard EV1 connector that you can get for a few bucks, which is nice. Now, since this fuel pump has an internal pressure regulator, the high pressure fuel will deadhead at the injector, and there's a possibility of an air pocket getting trapped in the fuel line. So, a setup like this needs to be purged of air. That's something to keep in mind. This is the MAP sensor we're going to be using. This guy is off of a 96 Saturn. Now, MAP stands for Manifold Absolute Pressure. So basically, this is an electronic vacuum sensor. The amount of vacuum in the intake manifold is proportional to the load on the engine. So the idea is to use this to detect the load on the engine and filter that through the Arduino and come up with a solution as to how much duty cycle we should send to the injector. This potentiometer has dual purposes. Initially, we're going to be using it to manually adjust the duty cycle for the injector just to get the engine running so we can collect some data. Once we have enough data and we're comfortable with the MAP sensor doing all the work, we'll use this potentiometer to fine-tune the system, like for cold starts and stuff. Now, for the injector, we're going to mount it to this 3D printed doohickey in front of the carburetor. Now, this doohickey is just a prototype, and the one we will use will be made of ASA plastic. That stuff has no problems with gasoline. So yeah, we're going to be using a carburetor basically just as a throttle body. There will be no gasoline in the carburetor and the engine will run directly off the fuel being injected. The reason we're going to be using the carburetor for now is I want to keep the governor linkages intact and I want the automatic speed regulation the governor offers. So this is pretty much all the stuff we'll use for our stupid simple small engine fuel injection system. Let's see if we can get it to work. Fast forward a little bit, and I have the system put together for our first test. The Arduino Uno microcomputer is actually hidden inside this very clever screw terminal shield. This guy was $38, but I love it and it's worth every penny. There's so much stuff going on that I absolutely need perfect connections, and this guy will do that very nicely. The potentiometer was mounted in an enclosure just to make it easy to get to, and I can just reach out and grab it without fiddling with things. This pot is temporarily configured to adjust the duty cycle of the injector for today's test. On the side of the enclosure, I mounted a button that we'll use for fuel prime on startup. Again, it's an easy to get to location. Now, to fire the injector, I'm using a generic FET transistor board. This board is definitely going to need a diode across the output to shunt the flyback voltages that are generated by the inductor inside the injector. Here's a snapshot of the injector signal without the diode across the output. Yikes, that's a huge spike. And here's a snapshot with the diode across the output of the transistor board. Yep, that's a lot better. I'll put the diode over here on the terminal board that feeds the injector, and that'll keep all the gizmos happy. This guy is a voltage regulator for the Arduino, and it's set for the typical 9 volts. Arduinos have an internal regulator that'll further drop the voltage down to 5, so we're good to go. This switch is wired to one of the digital inputs, and flipping it will tell the software to start sending a continuous frequency to the injector. Remember, this system's going to be running on a fixed frequency and an adjustable duty cycle to fire the injector. The code that makes this work is not very interesting, but I know some people want to see it, so stick around until after the credits roll and I'll do a quick walkthrough to show how all the software works. Future Jimbo here with a last minute edit. I show the map sensor right here, but that's a bad idea. You see, with the map sensor located far away from the engine, we're going to run into a big problem. It turns out a long vacuum hose can contain enough air volume to affect the way the engine runs. Keep in mind, we're dealing with a tiny displacement engine. The map sensor has to be as close as possible to the engine, but not directly connected to the intake manifold. And the reason is, we need to install this adjustable restrictor in the vacuum line to smooth out the vacuum signal. Using an adjustable restrictor is common when synchronizing carburetors on multi-cylinder engines, and it'll provide a nice steady vacuum signal. Anyway, it'll all make sense later in the video. Okay, for the vacuum port on the Predator engine, we're going to be using this carburetor adapter thingy. In this case, we're going to be using the normal Predator carburetor, and this gizmo would just be a vacuum port. Now, this hole is way too big, and if we use the stock Predator gasket, we'll have a vacuum leak. So, off camera, I went ahead and ginned up a Garolite reducer, and that'll allow us to use the standard Predator gasket. You know, a lot of what I'm doing today is a bit dodgy in the name of keeping stuff simple. I reckon once I get stuff sorted out, then I can go back and improve areas where we discover problems. This is normal for prototyping. Keep in mind, Ford didn't go from the Model T to the GT40 overnight. Nope, in between they built the Edsel and learned a few things. So, every step we take is a learning experience, that's for sure. Okay, we're set up to do some basic testing. Keep in mind, this is all kind of sketchy, and I do have a fire extinguisher handy just in case. Anyway, I ended up having to mount the map sensor as close as I could to the vacuum port on the engine. That way I could run a very short vacuum hose. Apparently, longer hoses make a big difference on such a small engine. I also have a vacuum gauge handy, and we'll need to look at that in a few moments. So the engine's set up with both fuel injection and a carburetor. The fuel injection stuff is ready to go. Everything is kind of hooked up in a safe way. The computer is powered up and it's in standby mode. Over on the laptop, I have the serial data going, and I want to capture the map sensor data while the engine's running on the carburetor. I need this data in order to write some more code, but no worries. We have enough junk and code in place right now to run the fuel injection. But first, we'll run the engine on the carburetor to collect some data. The high-pressure fuel pump is being controlled by this switch. Eventually, I'll have the computer control the fuel pump via a relay, but for today we're just going to be using this switch. So, flipping the switch will pressurize the system up to 40 psi, which is plenty of fuel pressure. Now, I'm using clear vinyl tubing for the low pressure feed and the vent lines. Vinyl tubing really should never be used with gasoline. I'm aware of that. Now, for the high pressure lines, I do have high pressure fuel hoses and tubing, so no worries. Alright, I'm going to start the engine with the carburetor and sort out a few things, then we can move on to the fuel injection. My first goal is to adjust the restrictor on the vacuum line to the map sensor and to the vacuum gauge in order to get a stable vacuum signal. A single-cylinder engine typically has a very jumpy vacuum signal, and we need to add some restriction in the line to stabilize the signal. It'll all make sense in a moment. Okay, let's fire this puppy up. So as you can see, the vacuum gauge is going completely nuts, and that's because it's a one-cylinder engine. The more cylinders you have, the more stable the vacuum signal will be. So with this hand, I'm adjusting the restrictor to slow down the signal, and wow, not much of a vacuum signal. We're showing 5 inches of mercury, and I was kind of hoping for 10 to 15. Now over on the laptop, that translates to 735 to 780 counts. I reckon I need to average this number with some more code, but it's good enough for now. Let me give the engine some throttle. The vacuum went down even more, which is to be expected. The laptop's now showing between 830 and 880 counts. Well, shoot, that's a very narrow map signal to work with. This is going to be interesting. Now, I apologize for the noisy test bench. Let me turn down the volume a little bit. Well, I think at this point we need to play around with the fuel injection. You know, just for fun. Now I could shut the engine off with this switch, but instead I'm going to shut off the fuel going to the carburetor, and then we'll let the engine consume anything that's remaining in the float chamber. Fast forward a minute or so, and the fuel in the carburetor has been completely consumed. Now this guy is the drain for the float chamber, and I'll remove the drain to make sure the bowl is completely empty. Boom, and just like that, the screw is out and the bowl is now bone dry. Perfect. So before we run the engine with the fuel injection, we need to bleed the air out of the lines. Pushing the prime button should clear the lines. Yep, we have fuel squirting. Very nice. Now if I flip this switch, that's going to command the injector to run continuously. And it does. It looks like that's a lot of fuel. Again, this is going to be interesting. Okay, let's put this all back together and hope for the best. Priming system. And the engine started from just the prime. Very nice. Let's try that again, but this time I'll try to keep the engine running just from the prime button. So that kind of worked, and the engine would have stayed running if I continued holding on to the prime button, so that's very promising. This time, let's see if the engine will run with this guy engaged. Turning this knob will modify the duty cycle on the injector. Turning it clockwise will make the engine run richer, and turning it counterclockwise will make the engine run leaner. So the engine's running, and I reckon you can see that. Now, I want to be clear, the engine is running on hard code and it's not running on any feedback from the map sensor. So yeah, it runs, but I haven't bridged the code yet, so it will run with the map sensor data yet. The scope is indicating about a 20% duty cycle, which seems like a lot of fuel for an engine with no load on it. Hopefully most of you folks can tell that there's something massively wrong with the way the engine's running. It's running rich and then back to normal and then rich again. But it is running, and I'll take that as a minor success for now. However, we clearly need to make some changes pronto. Again, it runs, but it runs terrible. Off camera, I went ahead and changed the frequency of the injector. Now, we started out at 30 Hz, and then I tried 60 Hz, and finally I went down to 15 Hz. The duty cycle had to be adjusted each time, but overall the engine ran the same, which is terrible. So it would appear we have gasoline pooling up in the injector adapter in front of the carburetor. I reckon that was to be expected. It's kind of a half-assed way to spray fuel. So yeah, it's kind of sloppy, it's spitty, it's drooling. I can even feel the fuel coming out of this doohickey. Well, it's obvious now that this was a bad idea. The injector really needs to be on the other side of the carburetor. I get that. Alright, watch how long the engine runs after I command the injector to stop squirting fuel. So it took a few seconds after the switch was flipped for the engine to stall. That's how much extra fuel was in the manifold. That's a problem for sure. This injector holder is less than ideal. Let's see if we can quickly come up with something better. So this is version 2. The injector will mount here and the air will come in through this hole. It's kind of janky, but I think it'll work. Now, it would be better if we mounted the injector on the other side of the carburetor, but for now, this simple injector holder will allow us to retain the governor linkages, and having a functional governor is awesome while I debug the system. So now the robot is working hard to make us the new part. We're printing this doohickey from Prusa ASA filament. This ASA stuff can handle gasoline and it's stable for elevated temperatures. The clock says we got an hour 51 minutes remaining. Time for a quick edit. And it's done. I love the fact that this part didn't exist 3 hours ago and now it's in my hand. You know, as a Gen Xer, this is pure magic. It's just like the replicator on Star Trek. Awesome. Fast forward a few minutes and now the new part is installed. This should get the fuel going in the right direction. It's not a perfect solution, but it's something we can use to troubleshoot the system, which we clearly need to do. Wow, right away I can tell this is so much better. So much better. Stupid simple? You got it. It's both stupid and simple. Let's take a look inside the manifold. Well, it's working. Okay, let me fiddle with the mixture. So I'm leaning out the mixture to see how much leaner I can make this. Well, that's about it. I would say this is too lean. Let me add a bit more fuel. So this is a bit complicated. Off camera, my right hand is on the fuel control knob and I'm adjusting the mixture manually. This new injector holder works 100% better. Just for fun, let's play with the mixture again. Whoops. So, a couple of things to keep in mind. The injector is still being manually controlled and the map sensor is not doing anything. Also, we're not running the engine under a load, so it's very easy to manually adjust the mixture. The new injector holder gives a much more stable operation. It's not perfect, but it's good enough to use in order to develop the code that I need to make the map sensor automatically regulate the injector duty cycle. Right now, well, we're still in the experimental stage and we don't have an active feedback control. Now, I do have a concern that I think I need to resolve before we go any further. You see, this spacer that we're using for a vacuum port is way too big. Now, what I mean by that is, this hole is huge, and if you recall, we had to use a Garolite shim in order to reduce the size of the hole in order for the gasket to work. Now, unfortunately, that leaves a fairly large cavity on the other side of the Garolite shim, which may be causing a problem known as wall wetting. It's hard to say if that's what's truly going on, but I feel like I need to go ahead and 3D print this spacer so it's a perfect match for the carburetor. Now, I could just 3D print a whole bunch of stuff, including an injector holder for that side of the carburetor, but I want to try this first in order to make sure that the ASA filament can handle the temperature of the cylinder head. I may have to use a Garolite spacer in order to shield the 3D printed part from the heat, and that's not a problem. Once I confirm that the 3D part can survive when exposed to the elevated temperatures of the cylinder head, then I have more freedom with the things that I can make. Anyway, I feel like this has to be done as the next major step before I start fiddling with the code. Let's turn the injector off and see what happens. Yep, that was a quick response, although there was a slight delay, and that may be due to wall wetting. Unfortunately, we sort of ran out of time this week, and today's Saturday and the video has to be uploaded tonight. This was a fun experiment and it does look promising. The goal, of course, is to keep this as simple as possible, and so far it's stupid simple as far as fuel injection goes. Fuel injection normally has a lot of components, and it'll be interesting to see if we can make this system work with just the map sensor as the feedback device. Speaking about feedback, I need feedback from the viewers. If you think we should take this to the next level and develop it so it actually works under a load and whatnot, if you think that's a good idea, click on the like button, and if you can, leave a comment like, yes, more. Or, hell no, I hate fuel injection. Either one's fine. As always, I appreciate the comments, and keep in mind, this is the stupid simple fuel injection we're working on. So less is better as far as parts go, and yep, I'm aware that more stuff would make it a lot better. The focus is on stupid simple and not stupid complex. Hopefully that makes sense. For those who are interested, stick around after the credits roll and I'll explain the code. It's real simple stuff and nothing groundbreaking, but some folks like to see that stuff. We'll see you next time. Until then. Okay, it looks like we got 4 people watching. Well, that's a bit more than I thought would show up. Anyway, the code for this gizmo is super simple, and the reason is, if possible, I want to replace the Arduino with a 555 timer circuit that's set up for a fixed frequency and variable duty cycle. So, the code is intended to pretty much mimic this circuit, but obviously the code's not finished yet. Anyway, I wanted to point out that I'm using the Timer1 library, which requires special syntax that the Arduino IDE doesn't recognize. So, in the library manager, you need to install the Timer1, which is not included with the standard IDE, but it is available with just a few clicks. So Timer1 is going to provide us with a way to set a fixed frequency on digital pin 9, and the duty cycle will be a variable number between 1 and 100, 1 being 1% and 100 being 100%. So the Timer1 library is no doubt using interrupts, and it more or less runs in the background, and we can feed it updated commands to modify the duty cycle. This cleans up the code because most of what Timer1 is doing is off screen. Right here I set the frequency to 10 Hz. Disregard this comment that says 30 Hz. In the setup, we have standard stuff, which also includes setup for the Timer1 that we're using. For debug, I'm sending this stuff to the serial display, and I'm sending it real fast in order not to upset the timing. Alright, let's move on to the main loop. VAC is the analog read for the map sensor. I'm not doing anything with this data yet, and it's just there so I can see it in counts on the serial port. Range is the analog read of the potentiometer. The number that we get from range will be between 0 and 1023, and obviously it's in counts. DS converts that range number into a half-ass percentage. It's sloppy math, I know it, and I'll fix it. Maybe. Run is the digital read on pin 4 on the Arduino. I'm using a pull-up on pin 4, so it naturally reports a digital 1. Flipping the run switch is going to ground pin 4, and this statement will happen. Basically, the statement is saying, apply a frequency to pin 9 at whatever duty cycle that the range on the potentiometer equals. Prime is a digital read on pin 3 on the Arduino, and again we're using a pull-up on this pin. When the prime button is pushed, then pin 3 will be a digital 0, and this statement will pulse the injector at 100% duty cycle. This will squirt gasoline into the intake port and get the engine primed for a startup. The last few lines of code are for debug. I have this silly little counter here, and when it gets to 100, the serial data will get sent to the screen. This is debug junk, and every 100 loops of the program will generate an update for the data. At the end of this update, I reset y to equal 0 and the count begins again. So basically, the main loop watches the analog signal from the potentiometer, and it looks for the command from the run switch and the command from the prime button. If the run command is received, then digital pin 9 will start spitting out a frequency with a duty cycle equivalent to the position of whatever the potentiometer is set to. I need to add code to average the map sensor readings, and I need to add the code that bridges the map sensor to the injector. My intention is to use simple math, and if that's possible, then we can get rid of the Arduino and use a modified version of this circuit. If the math gets kind of fuzzy, then I'll just keep the Arduino. Fuzzy numbers don't translate well to capacitors and resistors without a lot of effort. Anyway, that's the code, and I want to keep it as simple as possible, so ultimately I can get rid of it and just use hardware. Okay, it looks like we have one person left. I'm pretty sure that guy's asleep, so we'll just quietly end it here.